The second fundamental theorem of calculus states that if a function is continuous on an open interval containing a, then for every x in the interval, the derivative with respect to x of the definite integral from a to x, f of t dt, will always be equal to the original function f of x. Now that's really wordy, but basically what it's saying is this. If you take the derivative of an integral, it should bring you back to the original function. That makes sense, right?
Yeah.
We know that. We know that from the definition of just an indefinite integral. That, if we take the derivative of an integral, it should bring you back to the original function because they undo each other, the derivative and the integral. Something a little different happens when you apply the derivative to a definite integral, which is this case here. So basically what this does, in most of the time these are very easy to recognize because you're being asked to find the derivative of an integral. Also, they're typically given with respect to t rather than respect to x, but your final answer will have x's in them. So it's not just as easy as it looks. It does take a couple of examples for it to kind of sink in. So we're going to start with this example, which asks us to find the derivative of the function, the integral from 4 to x squared, square root of t dt. So we're being asked to find the derivative of that integral. So we're being asked to find the derivative of this integral. Now I'm going to take you through it the long way, and then I'm going to show you the shortcut for this that you can always use. Basically, if we just follow the instructions, if it says to find the derivative with respect to x of the integral from 4 to x squared of the square root of t dt. If we work that all the way out, we would first integrate the square root of t, and that would give us t to the what?
1/2 power.
Right now it's 1/2, so we add 1 to the power, and it would be 2/3 t to the 3/2, right? And we would evaluate that from 4 up to x squared. Now I haven't taken the derivative yet. I'm just trying to work on the integral, and then I'll take the derivative of the integral. If I substitute in x squared, I get 2/3 multiplied by x squared to the 3/2 power, which is what?
The square root of x cubed.
The square root of what?
X cubed.
Square root of x cubed, right? Is that right? Look, guys, if we put the x squared in, we would have 2/3 x squared to the 3/2. Right, you guys?
Right.
So it would really be just x to the what?
1/3.
No, how about to the 6/3? To the 6/2. It would just be x cubed, right? You multiply the exponents. So this part is going to make x cubed. So that would be 2/3 x cubed minus, we substitute in the 4, 2/3. The square root of 4 is 2, 2 cubed is 8. So we have the derivative with respect to x of 2/3 x cubed minus 16/3. So far so good, you guys? Tell me if I've made a mistake. Has everybody understood why this became x cubed?
Yeah, because you just multiply on the top and you get 6/2, which is the root.
Or another way of saying it is the square root of x squared raised to the 3rd power. Well, the square root of x squared is x, and x to the 3rd is x cubed. Okay, so we were okay with our integral, right? Now all you have to do is take the derivative of that answer. So what is the derivative of this answer?
2x squared. Yeah,
Guys.
2x squared
2x
minus
squared.
16/3x. No.
Not quite.
2x squared. Yeah, because we're not doing the rat, whatever.
2x squared, right? Right? Minus 0. Because the derivative of 16/3 is 0, right? So this answer should be 2x squared. Does everyone see how long it took us to get there? Hey, time out, guys. Does everyone see how long it took us to get there? Okay, we'll pause for a second and see if you have any questions. So here's a shortcut that will work every time. If you're being asked to find the derivative of an integral, which we are in this particular case, all you have to do is substitute the top number in to the original. So we'll substitute in the top, and instead of square root of t, we will have the square root of x squared. But the key is you have to multiply by the derivative of the upper limit there. So what's the derivative of x squared?
2x.
2x, okay. So you substitute the top number in, multiply by the derivative here, and then you subtract the bottom number substituted in, which is the square root of 4, and multiply by the derivative of the bottom number, which is 0. So what we have is the square root of x squared multiplied by 2x minus 0, which just gives us 2x squared. And that will work every time you're dealing with the second fundamental theorem of calculus, and you're being asked to evaluate the derivative of an integral. You don't actually have to do any work. All you have to do is take the top, substitute it in, multiply by the derivative of the top, the upper limit, then minus, substitute in the bottom, and multiply by the derivative of the bottom. You just have to be careful because the chain rule there is the only part of calculus you actually have to worry about. So that's where that 2x came from, and that's where the 0 came from. They are the derivatives of the upper and lower limits, respectively. So we're being asked to find the derivative with respect to x of the definite integral evaluated from -3 to 2x of t cubed minus 4 with respect to t. So since we're being asked to find the derivative of a definite integral, we can apply the second fundamental theorem of calculus, which states that all we have to do is substitute in the top number. So if I put the top number in for t, I get 2x quantity cubed, which is 8x cubed minus 4. And then we have to multiply that by the derivative of the upper limit, which is 2. So this is just the substitution. This is the derivative of the upper limit. Then we substitute the lower limit in, and -3 cubed is -27 minus 4. And then we multiply that by the derivative of the bottom, which is 0. So a lot of times your second part will 0 out if it's a constant. If it's another variable, it won't 0 out. So you have to be on the lookout for things like that. So this equals 16x cubed minus 8. And then this whole piece went to 0 because it was just a constant. And when we multiplied it by the derivative of that constant, it zeroed out. So if you work this the long way, if you integrated, substituted in f of b minus f of a, and then you took the derivative, you should get 16x cubed minus 8. For our final example, we want to find the derivative of the definite integral from -3 to cosine of x of 2 minus the cube root of t with respect to t. So applying the second fundamental theorem of calculus allows us simply to substitute in the cosine. So I have parentheses 2 minus the cube root of cosine of x. But I have to multiply that by the derivative of that upper limit. So what's the derivative of cosine of x?
Negative sine of x.
Negative sine of x. Minus, I'm going to substitute in the denominator. So I have 2 minus the cube root of -3 multiplied by the derivative of -3, which is 0. So this piece just zeroes out. And if you want, you can stop here. Because typically with derivatives, we do give them in factored form. Or, I left an x off. Or you could distribute, and you would have -2 sine x plus sine x multiplied by the cube root of cosine x. So they can look really ugly, but they're not actually that difficult to handle. And that's the second fundamental theorem of calculus.